Hi, everyone. This is Peter. I'm with Google. I'm sorry I can't be there in person, but I'm very excited to tell you about the progress that we've seen over the past almost 10 years in federated learning. So if you have any questions, please feel free to reach out to me. It's my last name at google.com. And without further ado, let's dive right in. But before we go into some of the recent advances, let's go back to pre-federated learning. Let's go back to 2016. And at that time, when we wanted to train AI models on user data, that's data that's created on device, the way we would do it is we would essentially centralize that data in the data center and then have an engineer submit an AI job that specifies the model and training algorithm. That training happens in the data center, and then the engineer gets the model checkpoints in the final model, does some A/B testing, and then if the model performs well, that engineer deploys it at scale to the devices. Now, the question that we asked ourselves at that point in time is, can we actually train high-quality AI models from on-device data without collecting the data, without centralizing it, essentially? And this is the added benefits of faster development, better battery life, and the most important one, the one that I'm going to anchor this talk on, is it has a lot of privacy advantages. And so this gave the birth of what we now know as federated learning. And in this talk, I'm going to focus on cross-device federated learning, but other speakers are going to talk about different flavors of federated learning. So in this setting, instead of centralizing the data and running the computation in the data center, rather, we actually push the computation to the device. As you can see on the slide, we are actually running the computation on the data, which lives on device and stays on device. And the server only gets to see updates that are focused and minimal from those devices. From the engineer's perspective, it is the exact same experience. It is, in fact, almost exactly the same API. They would submit that job, but little do they know that now, instead of the training happening in the data center, it's actually orchestrated across a very large fleet of devices. Think 10 million devices, maybe even 100 million devices. And really, federated learning, since its introduction in 2016-ish, it took off. And you can see this chart comparing the popularity of federated learning to differential privacy, which is a very popular privacy technique, which we're going to talk about as well in this talk. You can see that around 2019, the popularity of federated learning really took off and blew past of differential privacy. This just shows that FL is extremely useful and popular. There's a lot of activity, both in academia and also in industry. And one thing I'd like to point out is this definition of federated learning, which came about 3 years since its initial introduction. And we defined FL in the Advances and Open Problems in Federated Learning paper as a machine learning setting where multiple clients collaborate in solving an ML problem. And they do so under the coordination of a service provider. Each client's raw data is stored locally, never exchanged or transferred. Instead, only focused minimal updates that are intended for immediate aggregation are used to achieve this goal. Keep this definition in mind because we're going to come back to it and we're going to challenge it towards the end of this talk in the part where we do projections into the future. And the reason FL was so successful is because it gave a lot of teams at Google the ability to actually train models on data that is traditionally sensitive and is on device. And we don't collect it in the first place. We don't want to collect it. And this opened up a space of applications from health studies to Android's smart text selection to Google keyboards, emoji and sticker prediction to next word prediction to even Google's hot word detection for Hey Google. So you can see across the board, it improved our models and services for our users. And this indeed actually really became so meaningful because before federated learning, there was this general perception that either you wanted utility and you had to collect the sensitive data, centralize it, train on it so that you get improved services, or you wanted privacy. And that meant at that point in time, you just don't train. That's it. You don't improve the models and you don't train them on user data. And what if federated learning essentially did is that it introduced a new dimension to the privacy utility trade-off curve. It allowed us to actually improve both privacy and utility at the same time, unlocking new applications. But what we realized early on in the process is that privacy is neither binary nor even scalar. It actually means a lot of different things to a lot of people. And in one recent paper, which is called Federated Learning and Privacy, published in the Communications of the ACM, we tried to write down privacy principles that we believe are important for a lot of people and that separate apart different concerns from the perspective of the user, the platform, and the verifiers. So let me quickly walk you through these privacy principles. The first one is about transparency, is about auditability, and about controls. And it says that the users should have full transparency and knowledge into whether or not their data is used to improve the service, what purpose is it used for, and how is it used and being processed. And they should have the ability to revoke that access should they choose to. And this is usually done through very solid user interfaces and by actually telling the user exactly what's happening under the hood. The second privacy principle is about data minimization. And this says that whenever you want to compute in any user data, you should only access whatever is absolutely necessary at every stage of the computation. So this is about securing the data, encrypting end-to-end. This is about strict access controls, strict TTLs, and only sharing from one boundary to the other the strict minimum that is necessary for the continuation of that computation. The third privacy principle is about data anonymization. And this one is really mostly about the output of the computation. And it says that should an individual choose to participate in the computation, the impact of that individual on the output of the computation should not be drastic. So the computation should not overfit to any single individual. And this is usually satisfied with differential privacy and memorization, auditing techniques to kind of quantify it and measure it. The last privacy principle is that about verifiability. And it says that if a service provider makes privacy claims, let's say they claim they're using federated learning, differential privacy, or any of those technologies, you should be able to verify their claims. What level of differential privacy are you using? And how are you applying it? And what kind of noise are you adding? And where? And how are you minimizing data exposure? You should either be able to falsify the claims or verify that those claims are indeed correct. And all these privacy principles should come together to give a privacy in-depth solution to an AI training pipeline. Now, in the interest of time, I'm mostly going to touch in this talk on data minimization and data anonymization. Towards the end, I'll come back to verification and talk about it very little. But keep this picture in mind because it's important. And in particular, I do want to emphasize that when it comes to data minimization, you should view FL as a strict data minimization technology. As you can see on this slide, FL encodes minimized data exposure because it doesn't move the raw data to the server. It only sends focused updates. And in fact, those updates are made anonymous and ephemeral with respect to the server. They're not logged, they're not stored, they don't persist endlessly in some logs, they're immediately aggregated, and we only deploy just the final model, not the intermediate checkpoints at deployment time. So all these things are encoding data minimization. And we have also worked hard since more than 6 years to enhance the data minimization principles and technologies applied to FL using cryptography. One such technique that we built up is called secure aggregation. And secure aggregation allows a server to obtain the sum of high-dimensional vectors. These are client-held data in a way that ensures that the server learns just the sum and no individual data whatsoever. So this is quite important. These high-dimensional vectors are essentially the parameters of the model updates that each user is going to send back to the server. And we don't want the server to see the updates that are incoming from every client device. We want the server to only be able to learn the sum of those updates. And of course, it took many years and many iterations for us to perfect the system, to scale it up, to make it efficient, make it robust against malicious clients, against clients that can collude with the server, and to actually make it run at scale in production. I'm listing out 3 papers on this slide, including one that is very recent. I invite you to take a look at them if you want to know under the hood what's happening in this protocol, because it's a very complex protocol. Now, in addition to data minimization, I want to talk about data anonymization. And in fact, the bulk of this talk is going to focus on data anonymization. And with regards to data anonymization, memorization is the most important thing for us to understand. Here I'm showing on the left-hand side what I am calling good memorization. These are patterns in the training data that are very common across many individual users. And we want models that are trained to actually capture those patterns. You would like when you take your keyboard on your phone and type what have you for it to complete it with been up to, because that's a very common pattern that a lot of people who are English speakers use. Whereas on the right-hand side, if you take your keyboard and you type Alice's credit card number is, you definitely don't want the model to spit out Alice's credit card number. And that is because Alice's credit card number is only a number that Alice owns, but no other user in the data set should own or have. And if it happens to be the case, only very few users would have it. So we don't want the model to actually memorize those kinds of sequences. So that's the intuition. We want to prevent the memorization on the right-hand side. We want to allow for the memorization on the left-hand side. So how do we do it? There's this notion of user-level differential privacy, which says that if you take 2 data sets, and if these 2 data sets are identical except for one user, so D and D prime are exactly the same, they have all the same users except for one user, and you run a randomized training algorithm, you want the outputs of the randomized training algorithm on D versus D prime to look almost exactly the same. And the way we measure similarity here is using what's known as the max divergence or the infinity divergence or the hockey stick divergence for those of you who are in the information theory community. And we want the divergence between the distribution of M on D and M on D prime to be small in the epsilon delta sense. You should think of delta as something that is very cryptographically small, 10 to the negative 10 or even smaller. And you should think of epsilon as something that's in the single digits, preferably as close as possible to 1. And you can see that if this divergence is so small, then we cannot distinguish the distributions of M of D from M of D prime. These two are very close to each other. And the way we deploy differential privacy to FL is actually quite interesting. So first, let's look at how we train with FL. There's this very popular algorithm that's called the Federated averaging algorithm. And since its introduction in 2017, there's been a lot of improvements on it. There's literally hundreds, if not thousands, of papers that introduces many variants of this algorithm that improve upon it. But what this algorithm does is that it runs a number of SGD steps locally on the client's data. And then when we aggregate the updates across devices, we just simply do averaging of these updates. Sometimes we weight them by the number of examples that they were trained on. So that's why we call it federated averaging. The name is simply because we're just averaging on the server the model updates across clients. And the way to modify this algorithm to achieve differential privacy, you have to take my word for it. But if you do it, then you have to do two key steps. The first one is you have to bound the user contribution, and this is done by clipping the model update. This is usually by clipping the L2 norm of that vector that represents the parameters of the model update. And then when you've aggregated the clipped updates, you would add Gaussian noise. And that Gaussian noise would have a standard deviation that's actually proportional to the clipping norm that you've used, which is the sensitivity of that sum query. Simply by doing these two steps and iterating it, you achieve differential privacy. Now, even though the application seems very simple, there are many caveats in terms of how we compute the final epsilon and the delta, and how we achieve good epsilons and deltas. And I'm not going to talk extensively about those, and I'm just going to assume that this high-level presentation suffices for the understanding of how we add differential privacy to FL. But one might ask, what if I want to actually use secure aggregation and differential privacy together, and I want to reduce the amount of trust that I place in the server, meaning that on the previous slide, we were trusting that the server would add the noise on the behalf of the user. And on this slide, what I'm showing you is a high-level idea of how you can take that model update, which is represented via xi on this slide. This is after you finish training, and how you would first clip it to bound the user contribution, and then flatten it out via some random rotation, and then discretize it using scaling and randomized rounding, and then add integer noise locally to it before you actually do the secure aggregation process, which operates on integers modulo some prime number. Now, there are a lot of details on this slide and many, many caveats. And I'm not going to dive into all those details. I've listed out a long line of papers that our team and myself specifically have done in this space to build the algorithms, prove their security and privacy guarantees, scale them up, and show that they are optimal in some sense. And this is actually something that we've deployed in production. If you just Google distributed differential privacy for federated learning, you'll see a blog post that talks about how we've deployed this technology for Android's smart text selection. So this is not just something that we've researched and built, but we've also deployed it in production at scale. But here's something that we noticed once we started deploying this version of differential privacy. It turns out that there are a lot of challenges to achieve strong differential privacy in production. And that's one thing that we've hit a few years ago. And it's really related to the fact that in order to get very strong differential privacy guarantees, that's like really small epsilon, to make that divergence of these two distributions we talked about very close to each other, what you should do is you should sample clients at random in every training round. And when I say at random, it means from the total population. But in a system where you have hundreds of millions, if not billions of devices, each coming online and offline at random points in time, they can disappear, they can reappear. Even the server cannot track who is in the system and who is eligible, and cannot truly uniformly at random sample from those. So there are lots of challenges. I'm summarizing them in the box on the right-hand side. But the main one is that it's really difficult to be able to sample uniformly at random these clients. And that uniform sampling is important because it boosts the privacy guarantees that we can provide. It gives additional randomness that essentially allows us to prove better epsilons. So we wanted to address this problem, and we had to rethink everything from first principles. And one thing that allowed us to actually think through this problem from first principles is that if you take the federated averaging algorithm, and if you look at the update in round 4, if you just unroll the federated averaging algorithm, you'll notice that the update in round 4 is strictly a function of the sum of the updates in rounds 1 through 4. And the intuition you get from this very simple task is that what you should be doing is you should be trying to estimate the running sum of the aggregated updates across the rounds that have been executed so far. By simply looking at it as I'm trying to estimate with differential privacy the running sum, which we also call prefix sum, that allows us to tap on a new set of techniques and tools. Importantly, those techniques and tools do not rely on having to sample clients uniformly at random. And this led to the creation of the algorithms that are known as DP-FTRL. FTRL for follow the regularized leader. Now, I'm not going to dive into the technicalities here, but I'm going to compare left-hand side with right-hand side, because on the left-hand side, what we're trying to do is we're trying to estimate the aggregate of every round with differential privacy. This is nothing but what I showed you in the figure 2 slides ago, using the Gaussian mechanism and clipping. We're adding independent noise across all the training rounds, but we crucially need that sampling step in order to prove strong privacy guarantees. On the right-hand side, because we're viewing this as a streaming process, and we mostly care about estimating the running sum or the prefix sum of all the model updates we've seen so far, that allows us to use new protocols. One of them is called the tree aggregation protocol. More recently, we've developed the matrix factorization mechanisms applied to deep learning architectures. And what this amounts to is we end up adding correlated noise. Again, it's a streaming process. We're estimating a running sum. And it turns out that the best way of doing it is not by adding independent sum. It is by adding correlated noise. And that correlated noise has some structure that allows us to achieve better performance. And crucially, it is competitive with DP federated averaging, the protocol that I'm showing on the left-hand side, without having to use amplification. So it resolves that very difficult thing to achieve in production at scale. And we've worked really hard to perfect this mechanism. There's, again, a long line of papers that my colleagues at Google, myself included, have worked on over the years tirelessly to develop this protocol. And as a consequence, we are now at a point where we can train with federated learning and DP using a simple way to bound the user influence, to bound the number of times a user participates, for instance, at most once in 24 hours, and then at most, let's say, 6 times during the lifetime of the computation. And then we add this correlated noise, say on the server in this picture. This allows us to actually achieve strong differential privacy guarantees without sacrificing accuracy much. As a result, working with the Google keyboard team for more than 5 years now, we were able to announce that all their models, all the neural network models, are now trained with differential privacy and federated learning. All the data is kept on device. We've trained more than 30 Gboard models in more than 7 languages in over 15 countries. And what we were able to achieve is, in some cases, an epsilon that's strictly less than 1, which is the gold standard of differential privacy. That is a really hard to achieve epsilon, and a lot of people thought this would never even be possible to get good accuracy and at the same time get such strong epsilon. A lot of things had to happen. We had to scale our training to many, many more devices. We had to pre-train our models on public data. We had to perfect our mechanisms and use these DP-FTRL mechanisms with correlated noise. But we are now at a point where we can deploy federated learning with differential privacy at scale. So this is one of the biggest achievements when we reflect back and think about federated learning. There's obviously a lot more details and providing a lot more links, multiple blog posts, as you can see, in one research paper that is on arXiv that you can look at. But this is where we are today. We've come a long way. We can use secure aggregation. We can add differential privacy. We can extend the federated learning architecture to analytics and others. But there are still a lot of things that remain challenging. The technology needs to scale to many more applications. We need to be able to train many more models at once on every device across multiple apps. Think multiple Google apps or multiple whatever service provider apps that you have in mind. The models over the last 3-4 years have grown in size exponentially. Today, we train hundreds of billions of parameters, at least tens of billions of parameters, and everyone is excited about foundation models and large language models. And those present really tough challenges because we have limited compute, limited memory, and limited bandwidth. So it's difficult for us to actually ship these models, train them on device. We don't have enough bandwidth, compute, or memory. And that is a big challenge that I want to address in this talk. And finally, this privacy guarantee that I just talked about, the DP guarantee, still relies on the server adding that noise. And what I've just described, you saw on the last picture that the noise, this correlated noise structure, was actually applied by the server. And it's really difficult to decentralize it and do it very efficiently in a distributed fashion because it has correlated noise across routes. We have some recent work that looks into that, but it's really difficult to deploy it, and it needs a lot of improvements for it to become a thing that meshes well with multi-party computation and secure aggregation. And we are still not able to fully defend against Sybil attacks. So we need to actually improve things. And I want to dive a little bit into the LLMs picture because that is top of mind for me and for a lot of people as well. So what's happening these days is that there's an explosion of models that have increasingly more power, and they've really been a paradigm shift in the way we think about training models. Because rather than training individually for every single individual task with every single modality and every single language and so on and so forth, we now train one gigantic model, which we call a foundation model, which we then take and either prompt engineer or we fine-tune for given tasks. And I'm trying to summarize some of the activity in this space. Excuse me if I don't have the models. They would not fit on one slide. This keeps really changing very rapidly from one day to the other. But the point here is that this has been a radical change. And really what is common between all these models is that they've been trained on a lot of public data sets, web data sets. Think Wikipedia, news websites, blog posts, research papers, so on and so forth. But we know that there's a lot of data that is actually siloed that is just as crucial, if not even more crucial. Think medical patient data or biometric data, user location histories, user chats, emails, user calendars, financial data. If you really want to train a very smart personal assistant, you have to tap on calendars and chats and emails. Without such data, it's impossible for you to design a perfect personal assistant. It is impossible for you to design a perfect medical assistant or a financial assistant. So we really have to tap onto all these modalities and use them very, very cleverly. And that's why we have to train on non-public in-domain data. And that is the crux of why federated learning continues to be just as important. So let me overview how this can be done. On the right-hand side here, I'm showing very different training sources, all the way from public data. That's the data that we've essentially exhausted to train these large language models. We've even considered semi-public data, web scrapes, forum posts. They've been increasingly locked down. Stack Overflow, Reddit, Twitter, X, all these forums have been locking down their data. But in the past, we had access to them and people used to train on them. But then as you go deeper into that stack, you have centralized user data. Those are your emails and photos and search histories, so on and so forth. They're traditionally in the data center, but you can go one step below and you have the undevised user data. And that's data like text entries, swipes, clicks, location, speech, sensor data on your phone, so on and so forth. That is data that we don't even centralize. That is very personal, very sensitive, extremely on device. And we want to learn across all these modalities of sources. So for models, we have a similar hierarchy. We want to be able to train foundation models that are very large, multimodal, and multilingual. But these models are so large that they can only be trained and served in the data center. And that's why they're mostly trained on the primary two sources at the top of the hierarchy. But we've been interacting with these models for years now. Think ChatGPT and Gemini and Claude and all these models. We give them feedback. We give them thumbs up or down. We correct them when they make mistakes, so on and so forth. And that's why using things like instruction tuning and RLHF, we are able to improve these models on user prompts and user feedback. And so we already are incorporating in-domain user data into them, and we need to do it responsibly. But there's also a need for smaller models that are probably more task-specific, and they may still be large-ish, but they're not as large as those big foundation models. And those probably live in the data center. So these are distilled, fine-tuned models. And because they are task-specific, they really have to be trained on in-domain data, again, from either centralized or on-device data. Think here, for instance, if I want a model that is really good personal assistant or a really good medical assistant, I would have to take one of these foundation models, I would have to distill it down, I would have to fine-tune it on either financial data or medical data or personal data. Finally, there's these per-user models that are going to be extremely helpful for a variety of use cases and tasks. And these models are unique to us. So these are much, much smaller. These are on-device models. They interact either training or inference with a larger model to get help when and if they need to. So across the aisle, we need to figure out a way to evolve federated learning to help us incorporate these different data sources into the training stack of all these models at all these granularities. And this is a challenge, and this is where we are today. So we need to figure it out together. And that's why we recently proposed this definition of federated learning, where, again, it's a machine learning setting where multiple entities collaborate in solving a machine learning problem. But a complete FL system should enable clients to maintain full control over their data, the set of workloads that are allowed to access their data, the anonymization properties of the workloads. And FL systems should provide appropriate transparency and control and should allow the users to verify any claims. So this is a recent paper that we put out, which has the title of this talk that I'm giving. And this is a paper that talks about minimization, anonymization, verification, and also transparency and control. So this is how we want to think about FL, as an evolved definition that allows for all these things. And before I close, I want to give you an example of how we might achieve it. So we're thinking a lot about using trusted execution environments, which allow us to prove that we run a specific binary securely on a specific CPU. So we can create a chain of trust extending from client devices to server-side trusted execution environments. This enables us to prove statements such as data from individual devices will not be visible to the server, and only anonymous aggregates that are computed with differential privacy subject to TE correctness will be actually revealed to that data analyst that has requested them. So we go into the details of this system, of how we can design it. And again, one of our very recent papers, it's called Confidential Federated Computations. There are lots of interesting details in it. But at a high level, just to overview the system, the way it works is that instead of actually pushing that very large model to the device, which, as I said before, we don't have enough compute, memory, or bandwidth to do it, because now the model is much, much, much larger than the data itself. What we would do is we would use a verified public key that we get from a TE-hosted ledger in order to encrypt the data and send it to the service provider. So the service provider will get only encrypted data. It cannot access that data. It cannot decrypt that data. It needs the key that is held inside of a TEE that it cannot access in order to decrypt that data. So it's only when you want to run a computation, you move the encrypted data from storage into a TEE that hosts the workload. And inside of that TEE, you have access to the key that's needed to decrypt the data, run the computation, add verified differential privacy to it, and then release only the aggregate. And we should be able to attest across all the stages of this computation that everything is working as intended, that privacy is indeed added via the claims that we are making. Now, I've left out a lot of details because I wanted to project and show you this future of federated learning. This is something we're working tirelessly on and scaling up. It's a very new system that we think is going to allow us to run computations at scale. It is done a little differently from the classical notion of FL, but it still preserves, in fact, it reinforces the main privacy principles of FL. So with that, I'll stop. And if you have any questions, please feel free to shoot me an email. Thanks so much.